Alright guys, welcome back to part 2 of HPLC column lecture. I'll just put that one in for the sake of... Alright, so we talk about the limitation in terms of pH just now before entering the second part. Alright, so since we now know that silica oxide has some limitations, so what can you do about it? So there are advancement in terms of support type development. For example, cross-linking polymer materials that are being used. So you can have polystyrene divinyl benzene materials, or you can have polyether or polymetallic methacrylate (PMM) to as an ingredient, as part of the component, to make sure that the silica now is more resistant to, say, for example, pH or even temperature. Okay, so and at the same time you can produce the materials that is now good for biomolecule separation. Say for example, if you want to separate an enzyme from the stomach. Okay, so stomach pH is lower than between 1 to 2, and you don't want to run your purification at a high pH because you might denature the enzyme. So therefore, you really want to run it at a very, very low pH. So having a polymer materials as part of your silica components can actually create a resistance to extreme pH, and therefore you can now use it. Alright. So the wide pH range. So it also means that you cannot have the cyanol groups freely available inside your column. Alright. So other bonding materials are such as using alumina for encapping or for different purposes, because as for example, we have a thin layer chromatography, right? So it's still a chromatography. It's not HPLC, of course, but it's still part of chromatography, and you use alumina to bond the silica with the aluminum plate. Alright. It also says it's very common for silica gel chromatography, whereby you have alumina in there. So depending on your purchase, you can actually read if there's written there with alumina or without alumina, or different metals altogether. Okay, you can also have a zirconia type material for temperature stability, but that one is very expensive. It's just based on the name, that it's type of like a diamond kind, and what you can have now is, since you can have a polymer on your silica, it doesn't mean that you will replace the silica altogether. No, it means that it's an additive for the silica. Now you can have a more resistant column. So that's why in my case, I normally just buy a normal silica, even if I want to increase the temperature to about, say, 40 or 50 degrees for my purification or analysis. Okay. So having this type of materials can give a certain resistance towards temperature and pH for your column, so that you will have a longer half-life. Alright, so some example is that if you modify it with just C18, you become very hydrophobic. Okay, it's very high retentive and a very stable reverse phase. Okay, so first choice for most separation of small molecules. I cannot say for most separation because it doesn't always the case. Small molecules that are, I would say, not too polar and not too non-polar. Say for example, if you want to prep a lipid, if you want to purify a lipid, okay, a lipid which has a very long alkyl chain, for example. Okay, so you have phospholipids. So which type of silica support you should use? Should you use C18 or C8? Of course, the answer is C8 or even C4. Why? Because if you have like for example, this one is a C18 column, if you do have a C18 lipids that you want to purify, what might happen is now, because of the high forces that is being developed between your silica, if I were to draw it like this, okay, your C18 silica and your, so that one is silica, okay, imagine that this is your silica particle, and your lipids, okay, because they can have like a similar length, you can have like an extreme attraction between those two, and therefore it will never actually segregate. Okay, this happens before. When I was doing my PhD, some of my colleagues accidentally uses a C18 column to purify lipids, and you pretty much you cannot recover the whole system altogether. You can try to recover it, but it's very difficult, and now it will definitely impact on the performance of the column. Okay, similarly, if you have C8, so it will have a lower non-polar attraction or forces, so you can have cyanide, phenyl, C4, C3, or even less on the usage. So you need to understand what you want or what your company wants, do your research, and decide on which type of column you want to purchase. Alright, so this is an example of a modification or impact of different types of surface modified silica and the column separation, the resolution of your samples. So now you have 5 samples over here. I'm not sure if you guys can see it. I'll just zoom a little bit. Okay, so you have 5, 1, 2, 3, 4, and 5, and over here is to show you the structure of the 5 components. Okay, you can see they are rather similar, but at the same time different. For example, that's the basic structure, just a toluene with one resin ring with a metal group. Okay, and once you move up to once you move to compound number 1, now you have additional functional groups. Move to compound number 2, where you have an amine here and just a carbon over there. You move to compound number 4, now you have di-substituted amine and additional of an amine group in the middle of the structure. And moving to number 5, or for number 4, you just have the di-substitution but no amine. So the structure of the molecule, I would say, if you were thinking about just the structure, ignoring the atoms that is being used, they are almost identical. But using different types of silica modified surface, you can have different types of separation. Okay, and of course you can see here C18 gives you the best resolution, whereby you can clearly see all 5 compounds are now reasonably separated, and by using a C8, or if you were to purify this, then now you can do it in a better way. Okay? So you can just click on that one, like this, because there's a clear separation between the peaks. Okay? But rather, if you use a cyanide modified surface, 5 and 4 are quite close to one another. So when you are doing a collection, you might have a little bit of 4 in 5 or 5 in 4. Okay. Similarly, if you have phenyl, you can see that those two are still close to one another. So a single atom modification over here can have an impact on the characteristics of the spectrum, that, and of course the purification of your sample. Alright, so moving on, other than different types of materials or surface modification, now we move into particle size, or can be also abbreviated in a lot of literature as d small p, okay, subscript p. So what does particle size do? As I mentioned previously, it determines column efficiency and also back pressure. So smaller particle size, meaning you have a small void volume, and therefore you have a higher back pressure, okay, but you might have a better efficiency. So particle size, the efficiency is based on Vandermeer plot, as shown on the right hand side. Okay, yep. Alright, so that is a typical Vandermeer plot. So whereby the equation is H, peak height. On the y-axis, I'm sure Dr. Mugunda have covered this in his lecture. You have A plane, A term, B term, and C term. In that particular equation, A plus B over mu plus C times mu. And from there, you can say that the C term is directly proportional to particle size. Okay, so less efficiency loss at high velocity volume. So you need to consider the velocity volume, which is mu. Alright, so just based on this graph, how can I say, how do you determine that? So basically, it was determined based on a real experimental values. Okay, so whereby I can't remember which data is sourced from, but regardless, when you change the particle size from 10 to 5 to 3 to 1.9, you actually changes the Vandermeer plots. Okay, and therefore the C term is the so A term and B term is more of a flat influence, so it doesn't really influence the peak height, and regardless of if you change the linear velocity, it's a C term that influences the relationship between peak height and the linear velocity. So therefore, changing the particle size, if you can clearly see that you're actually changing the C term a lot. Okay, C term is the what do you call it, the slope. Okay, you are changing the slope very much. However, the operational pressure equation, so this is the equation over here. I'm not sure whether you have covered this. If you have not, do let me know, then probably I can just touch a little bit in the next lecture. Otherwise, it's all good. It tells us that the back pressure, so the change of pressure is back pressure. The back pressure is inversely proportional to, that one should be a small p, okay, to the particle size. So it's good in terms of separation, efficiency, but at the same time you have a higher back pressure. So in case whereby you have an old system that cannot accommodate very high back pressure, so you need to make sure that the particles that the column that you have does not use the smallest particle available. Okay, so using 5 or 3 microns are actually more than enough for most purposes, but you might want to go down to 1.9 depending on if you have ultra HPLC system. Okay, so therefore less than 3 micron particle can easily exceed 6000 psi in most HPLC system. Okay, most HPLC, but if you're talking about HPLC, it's a different story altogether. Okay, HPLC can handles some system that I've used can handles up to 20,000 psi. Alright, so some examples of the influence of particle size in column separation. Okay, so there's two graphs on the left hand side, on the right hand side. So what's important over here is to look at a clear separation or a clear differentiation in terms of the particle size. Okay, so you have 10 microns, 3 microns, and 1.7 microns, and you can see if you can actually combine. Okay, imagine if you have all this figure on top of one another, you can actually see the smaller particle size, you actually get a better resolution. So resolution is the highest, right? So this is the highest resolution. Of course, you also have the best efficiency. The best efficiency because now you can see you can have a better plate number, and therefore the sharpness of the peak is better. So if you were to just look at one of the peak, okay, so if you have 10 microns, is the width is that much. When you have 5 microns, the width is getting smaller, and then as you go down and down, you can actually see the width is getting smaller and smaller. So you're actually increasing the efficiency. At the same time, the sensitivity is also changes. So sensitivity in this plot is by looking at the y-axis. Okay, so these samples are all injected at the same amount, but if I zoom in a little bit over here, if you were to look at the first peak over here, the first one, the detection limit is 0.0, or roughly about 0.02. Okay, but as you go down, you can see now it goes slightly above than 0.02, and then now it goes close to 0.04, and then finally when you have the smallest particle, the resolution, the sensitivity, even though you are using the same equipment. Okay, so we are not changing the equipment at all. Of course, if you change the detector, you can have a different resolution, sensitivity, but in this case everything is identical, and you just change the particle size. Okay, by changing the particle size, you can actually get better resolution. So that's the main take-home point from this particular slide. Okay, and then finally, pore size, or can also abbreviate it as D pore, as shown here. Okay, most HPLC column uses porous materials because that's the oldest technology. So everything that deviates from the original technology becomes more expensive because it's now becomes new technology. So most HPLC columns still uses porous materials, and of course the materials that they are using are still silica dioxide, okay, as the core material. And the good thing about porous material is it increases the surface area. So increasing surface area increases retention, better retention, better resolution. Okay, so resolution meaning that you can separate. Well, of course the outcome is that you have a slower transfer time, meaning that each separation now takes a longer time, and if, say for example, the however bit over there is, if however the small pore is now being blocked by a big molecules or micromolecules. For example, as I give an example previously, lipids, a very common example. So the trapped molecule will now reduce the efficiency, becomes slower. So imagine initially if you have, say, if I were to give a number, 100 pores, even though it's illogical, but just bear with me, it's a theoretical perspective. If initially you have 100 pores, and once you run your micromolecules, the big molecules, it blocks 50 of those pores, what will happen? Of course, the flow rate of your sample becomes very slow. Okay, so slower transfer. If you want to separate a molecule, your flow rate of your sample might still be similar. Sorry, the flow of your solvent might still be similar, because imagine solvent has a very, very tiny small size. Okay, we are not talking about big solvents. So small solvents, like for example if you're using water or methanol. Okay, so the flow rate of the solvent might still be equal or identical compared to an unblocked column. However, because now the pores have been blocked, you now have a slower transfer rate, meaning that your samples, when it runs through the column, becomes slower and slower. Okay, and therefore leads to peak broadening, or peak or band broadening, okay, regardless of whatever. Okay, and this picture on the right hand side is an example of the spherical particles. You can see it's roughly spherical. It's not really spherical, but it's roughly spherical, and you can see there's a lot of the surface area is now increased. Okay, it's not a glass shape. I'm looking for like a ball where you don't have any pores at all, so you can actually have a lot of holes or spaces in between your sign out your silica network. That's the word. Alright, so an example of the influence of pore size, again over here. So ignore the original name, so discovery Ascentes, discovery below white and whatnot. So those are the terminology that the manufacturer uses to differentiate between the pore size. So what's important in this slide is to look at the pore size. Okay, 100 Armstrong, 180 Armstrong, and 300 Armstrong. So it also influences the surface area. Okay, as you can see, the surface area now becomes bigger and bigger, but at the same time, so you can see, if you still consider the same thing, okay, sensitivity, resolution, and efficiency. The sensitivity, or because we don't have the y-axis, I cannot really tell about the sensitivity of changing the pore size, which is fine. So the resolution, if you can see, the bigger the pore size, the less the resolution is. Okay, resolution is the key differentiation factor between two main peaks. So if you see here, now the peaks are getting closer and closer. Alright, so it's reducing the resolution. Okay, so resolution decrease as pore the pore increases. Okay, and finally, efficiency of the column is now I would say still okay. The efficiency, because efficiency is again depends on time requires per run. As you can see, if you just look at time wise, then of course the bigger particle size, the bigger pore size uses will allow for faster molecule transfer between the inlet and the outlet. However, you are reducing the resolution. Okay, so you need to have a balance. Normally you will use 100 Armstrong. That's a very common one, but in case if you were to purify a lot of compounds, you might want to consider a bigger pore size so that you can load more samples and have an average of everything. Alright, so you want to sacrifice your resolution for a better sensitivity, for example, or a better loading. So because there are so many variables that you can choose from, so that's why it's very important. As I mentioned, you need to do your research before you decide on which column you want to purchase. Alright, and finally, we will look at the column trend. So understanding the column trend is also important, since new technologies keep on coming out. It's rapidly evolving. I'm not sure whether it's rapidly evolving now due to COVID, but previously it's very rapid. Rapid based on the surface modification, size, the particle size, the pore size, the HPLC itself, whether it can withstand high back pressure. So if your HPLC can withstand high back pressure, you want to go for a smaller particle size. So there's a lot of things to know and to consider. So when I was doing my PhD, I was not exposed to all this information, so that's why I decided to give this information as part of the lecture, so that you at least know what are the key information that you need to look for in case if you are working with HPLC and your boss or you yourself decided to buy a new column. Okay, so of course the main outcome of this technology is to have a higher performance. Everything nowadays requires high throughput, so you want to have a high performance. and a more consistency results, meaning that if you have a sample on day one, and you get a certain peak retention time, peak height and whatnot, you want to still have the same identical peak in day say 30 or 40, okay, in case if you need to do replicates, or if you have a customer that requires you to analyze a different batch of samples, so you want to have a consistency in your spectrum. Okay, and this trend mostly resolve around silica modification, and of course, as I mentioned, because the topic is very broad, I try to narrow it down to silica based reverse phase column only. Alright, so now why do we need to have a modification? Why does the technology keep on rapidly evolving? So there are four main problems, and some of these problems have been touched or have been said previously. The first one is batch to batch consistency. So this is not just about consistency in terms of when you are running it using the same column. This inconsistency also reflects on the material when they are produced. Say for example, if I were to produce one particle now today, okay, so I might have a pore size of say 3 microns, but if I were to produce it tomorrow or the day after, will I get an identical particle size or a different particle size? So these are a lot of it plays a lot more on the column producer, not for you yourself, because normally as a user you just buy one column, you stick to it until it's damaged, and then you buy another one which might have a better resolution or a similar identity, so that you can do a comparison between your old samples. Okay, so those are on the user side. But this batch to batch inconsistency is talking about inconsistencies in producing the particle itself that is being used in the column. Right. Additionally, you might have a peak tailing for basic analyte. So I might have a slide based on that. Okay, so if you change your analyte from acidic analyte to a basic analyte, you might get a tailing. Alright, I'm not sure if Dr. Muguna have covered it in his lecture. Again, if it's not being covered, do let me know, email me or WhatsApp or whatever, so that I can probably touch about this particular aspect. And also low column lifetime. So the column lifetime has a lot of influences. Like for example, it's related to pH. So if say the column can handle a pH between 2 to 8, but then for your usage you normally use 14 or extreme pHs, whether it's acidic extreme or a basic extreme, so you might lower down the lifetime of the column. Thus there's modification or there's advances in the technology that is used to create the particle. And also what it means here is low column lifetime is that, what was it? I forgot. Sorry about it. I'll pause this, and if I recall that. Okay. Alright. So the low column lifetime can also means that when in a part 1 of the lecture where I touch about the sinyl groups. Okay. So if you do have a free sinyl groups in your silica particle, then of course you can have interaction or a reactive interaction with some other components or your analytes that you want to analyze, and therefore reducing the column efficiency and whatnot. Okay, so reducing efficiency, reducing the lifetime. Okay, so this particular trend section we looked at some key examples, including high purity silica synthesis. Of course it's very brief, it's not in very detail. You can always learn about this in very brief, and then if you're interested, then of course go into the literature and find more additional information. Okay, so first one is high purity silica synthesis. You can also look at hybrid particles, whereby you are not only using silica as the component, you are now adding in additional, like for example bonding reagent, you have polymer, so those are what I call as hybrid. Okay, and of course finally you might also have a novel binding chemistries that are involved in producing a more unique surface silica. Okay, and additionally, while talking about these three topics, I might touch a little bit on their impacts in column performance by, as you showed previously, I've shown you a lot of chromatograms on the impact of changing particle size and whatnot. Alright, so column trend high purity silica. So the early development of silica was I'm not sure, it's about 1970s. Okay, it's not until about in 1990s where high purity silica 99.995% with less than 50 ppm of metals were able to be produced in a batch to batch reproducibility and peak shapes. Okay, what do I mean by that is that so you normally when you have a silica reaction, you want to use some metals as catalyst. Okay, so previously the issue is how do you remove the metals, or if you were even if you were to remove it, how can you make sure that in batch to batch synthesis the metal component are equal or similar. As you can see, even at 99.99% purity, you still have about 50 ppm of metals as the highest. So instead, the industry put a standard: as long as the metal content is less than 50 ppm, it's all good. Okay, so if today you manage to synthesize high purity silica at say 40%, 40 ppm, and tomorrow you manage to synthesize at 20 ppm, that is already good enough. Okay, so it will still be considered as batch to batch reproducibility. And of course, all of this information you should be able to get it from the manufacturer itself. So if you were thinking about, I need to make sure that I have the almost identical column for whatever reason, you can always look at the pamphlet that normally comes with the HPL the column, and if it's not there, you can always go to your supplier and ask for this particular information, because it's part of a QC, QA and QC of a manufacturing to have all this information available. But whether they are actually telling you guys about the information or not, that's a different story. So but you can always go and request for those information. Alright, and what it means by peak shape of this basic analyze is like this. So previously when I always drawn this type of free cyanol group. Okay, but what you can also have is a geminal type, whereby one silica will have two hydroxyl groups, or even you can have an associated cyanol groups whereby you have an O in the middle. Okay, and they are kind of like bonded to one another, and they are normally associated. Therefore, when you do a reaction, they are very less reactive and whatnot. Okay, so schematic of various types of phenol and their relative acidities. Note that the cyanol can be activated by an adjacent metal group, adapted and reprinted from permission or reference number 2. Okay, so this one is from the book, from the book. Okay. All right. Next slide. So this figure shows you a comparative chromatogram showing the effect of silica purity on the peak shapes of basic analyte. Alright, so again, why do you consider basic analyte? Meaning that you are changing pH and whatnot. Okay, so which is important. And this figure is showing you, so you can see the plate number is similar, flow rate is similar, mobile phase is constant, basic analyte is those two. Okay, number 4 and number 2. And by just looking at a different quality, so this one is different company. Okay, so different company producing different types of silica, so one has a better resolution, even though both silica are surface modified with C18. You can see there both are C18, but you can have a different spectrum altogether. Okay, so it's very, very critical if you are working in a company that does analysis as part of the company portfolio. It's very critical for you to use different brand of column each time when you switch to a different column. Okay, so because you want to do a comparison as a company, what you want to do is you want to do a comparison. You want to be able to do a reproducible results. So if you have a client that sends you a sample every month one sample or so, you don't want to change your column, because once you change your column, then you need to re-optimize everything. There's a lot of time spent that needs to be spent to make sure that the spectrum can really identify the things that the client wants. So say for example, if you work with water symmetry C18 for your analysis, you as best as you can, you want to keep on using the same column so that you can have the same reproducible results. Okay, if you can't read that one. Okay, all right. So on the left hand side, as I mentioned, as you probably have guessed, not mentioned, if you already have guessed, is the high purity silica, and on the right hand side where you see the tailing of the peak is the less or a reduced purity silica purity. And not to say bad about the companies, but this is what happens, and therefore you need to always do your research before buying a column. Alright, so hybrid particles. In the silica synthesis of the first commercial hybrid particles, for example, written here is waters, but in the next slide there are a few more different brands of hybrid particles. It's mixed with methyl triethoxysilane, resulting in a hybrid silica support with 50% less surface cyanols. So again, what you want for a reverse phase is you want to have the smaller number of cyanol groups possible. Okay, of course this one is before surface modification, so you can already control, you can already reduce the number of cyanols, because imagine about this. Okay, if initially you have 10 of these cyanol groups, and then you do your surface modification first, and then you do end capping. So you can do that path. Okay, so you do surface modification and then you do end capping. But what might happen is that your surface modification is already bulk enough that when you do your end capping, some of the cyanol groups were not end capped properly. Okay, because of steric hindrance and whatnot. So if you have something like that, if you start off with surface modified and then you end capped, but you still have available cyanol, then the quality of the column that you're going to produce is actually quite weak. Alright, so in this particular technology, what they are doing is that they are reducing the number of available cyanol groups first. So again, if you were to consider 10 surfaces, they already reduce it to 5. Okay, reduce it by 50%. Now you have 5. So imagine if you have these 5 cyanols which are well separated between one another. Now if you were to do a surface modification, you might be able to get 100% substitution. Okay, so that is the critical information about hybrid particles. So less individual cyanols activity, less peak tailing for basic analytes, and of course if you have less cyanol groups, you have a wider usable pH range. Okay, it's mentioned here is 2 to 12. It can be 1 to 13 for all we know. Okay, so this is just an example. Okay, so these are some other examples of an hybrid particles that are currently on the market itself. You can see these are the commercial names. So if you have used HPLC before, you normally you must have heard about Zorbax, Eclipse XBD, Luna Technology, Polaris. What else have I heard? Chromolith or Monolith. Okay, Vidac. So these are some of the names if you have used hybrid particle before. So previously you might not know that it's a hybrid technology. You don't even want to care about the technology because you are a user. In my case, when I was learning, I never actually know what those particular name means, but now I've learned. Okay, and again, as I mentioned previously, what you do is when you have this one is untreated, whereby you have you know, the most silica surface available before you do your surface modification. But this one is once you have modified using the hybrid technology, whereby now you have a less number of available silanols that you might or you might not want to react with the bonding agent to, you know, change the surface area of your silica. Right, so moving on to the final section, if I'm not mistaken. Okay, so we're talking about the novel chemistry involved in the trend on column development. So traditional bonding chemistry uses a monofunctional silane, achieve a maximum bonding efficiency of about 50%. Okay, these bonded phases suffers from several disadvantages. For example, at lower pH, the SI bond is subject to acidic hydrolytic cleavage, so it is very easily degraded. Or even if a high pH, the silica particle tends to start to dissolve. Okay, so any unbonded acidic cyanols might lead to peak tailing of basic analyte, or you might have a different reaction happening altogether that finally blocks the column, or changing the nature of the column itself. Okay, so those are some of the issues. So in order for the manufacturer to reduce or to mitigate these problems, so I'll give you like 3 examples that you can do. The first one is to use a sterically hindered group. Okay, for example, a bulky diisopropyl or diisobutyl groups that are incorporated as part of your bonding agent. Okay, as you can see in example down here, so of course initially you have just 3 cyanyl groups. Okay, and previously you might just want to react the cyanyl group with, for example, the C18. Okay, so you have that one, but C18 is not bulky enough to actually stops the middle cyanyl groups from reacting. So in order for the technology to evolve is by introducing this propyl moiety as part of the component. So as you can see here, that's the isopropyl, or you can have diisobutyl over there as part of the component. So even if the middle cyanyl groups are free as an cyanols, now because of the sterics hindrance available, the functional group is no longer as reactive. Okay, I'm not saying it's no longer reactive, because it's still reactive, but it's no longer as reactive, in contrast to if you have like a space allocated for a space that allows for a reaction to occur. Okay, so that's one way to do it. Second way is you can use a polyfunctional silane chemistry, whereby you can react more than one sinyl groups to achieve the same outcome. So what it means here now is shown as an example here is to use a difunctional or even trifunctional silanes for your surface modification. Right? So as an example here is that instead of having a phenyl like that on the previous slide, what you have now is, oops, why cannot I erase this? Oh, somehow I cannot erase this anymore. Anyhow, probably change the color then. Okay, so what you have now is a reaction with two functional groups of the silane. So imagine you have three again, you can have two of them reacting, and then this one is either you encap it, or if you do have another cyanyl group over here, you might have another reaction over there. So towards the end of the day, you will be able to minimize the free available cyanyl groups. Okay, it says here, however, polyfunctional silane chemistry is more difficult to control. Okay, because again, the technology is rapidly evolving, so the technology is now there. It can be, people can produce this, but it's more difficult to control as contrast to if you were to use a bifunctional sorry, not bifunctional, a bulky materials in it altogether. And the third one is, what you can do is you can do a polar embedded groups. So you can incorporate, for example, a polar group carbamate, amide, urea, ether, sulfonamide in the hydrophobic chain of the bonding reagent, so that it can produce some shielding effect of the residual sinyl. Okay, so it's pretty much kind of like creating a buffer layer in your synthesis, or in your columns, in your particle synthesis. But again, these are some of the exposure that you might be interested in, depending on what type of column you want to use for whatever purpose. Okay, and of course, if you do something like this, the selectivity is now being changed. So if you use a more say for example carbamide, then it will be more on acid resistance. If you use urea or amide, it is more on basic resistance. Alright, so this is an example of a different type of modified, I can't remember what type of modification is this. Conservativity various polar embedded, so polar embedded bonded functional groups. Okay, versus Luna C18 is a more conventional straightforward C18 chemistry. So this one is a more straightforward C18 chemistry where you don't have all the steric hindrance and whatnot. Okay, so Luna is at the very bottom down there. And if you still consider our three thing, sensitivity, resolution, and what's the other one? Sensitivity, resolution, oh god, I can't remember, even though it's previously. Selectivity, wait, was it selectivity? Alright, and the third one is efficiency. Okay, if you consider those three, And because this graph is a comparison with Luna C18, so what you can say about the SRE is that if you switch from Luna to MI RP C18 column, you actually get, of course, sensitivity. We cannot really tell because there's no y-axis values, so I can't really tell whether which one is better. The resolution itself is more or less the same, okay, because you can actually separate individual components. So in this case, in this particular case, resolution is equal. I would say more or less equal for everything, right? But the efficiency now is different, okay? Initially, it takes you 6 minutes to complete a whole cycle, but now for the first one, for the MI one, now it takes slightly more than 5 minutes to actually complete the whole cycle. So it increases the efficiency while keeping the resolution equal. Of course, you cannot talk about sensitivity. Alright, and the same criteria you can tell for the symmetric shield C18 and the acclaimed polar advantage sulfonamide modification. Alright, so you have more retention over here, less retention at the top, and this influences the efficiency of the run. Alright, so what are other modifications that are available other than, you know, we just keep on talking about the surface silica, the spherical silica. So there are some other technology that resolve around the use of different types of material altogether. So the traditional ones and the most widely used even nowadays are the spherical shaped bits or particles. So if you actually zoom in, you can actually see something like that. But of course, if you zoom in a little bit more, you can actually see it's kind of like a gauze with a lot of ridges for the pores. Okay, so although this type of materials works fine, so there's no issue with it because of the other technologies that resolves around using the spherical shaped particles, but it has a high void volume. As I mentioned, if you have high void volume, there are issues related to it. So instead of just minimizing the particle size, a new technology that is developed is next slide. Okay, so this one is just talking about general overview. So R&D minimizing the void volume but keeps or improve the color efficiency and resolution. Okay, so the ways to do it is by having a monolithic technology whereby what it does is the pores are being developed in the column itself. So instead of producing the silica outside and then putting it into the column, so the common technology was to fabricate a capillary inside the column. So capillary meaning that it's not a straight chain capillary, it's more on creating the void volume once it's already inside the column. So it's a radical departure from packed type column because it uses in situ, as I mentioned, to form the continuous bed of porous silica inside the fused silica capillary. So instead of previously whereby you packed in the spherical silica like this and having this void volume, what you do is you create the void volume after you packed it. Okay, so in situ. So advantage of Chromolith, Chromolith is a brand by Merck, is that the lower bed pressure, it produces lower bed pressure, which is acclaimed by the manufacturer to have a performance of a 3 micron particle even if you are using a 5 micron. Okay, so that is the claim that the manufacturer do. Of course, normally they do have research division that shows you know, as what I've shown you before, this graph is better than that, better than this and that. Okay, Unfortunately, I do not have the figure using the original technology. Okay, so this slide is kind of like a bit off because I cannot do a comparison. I cannot find it, but this is just to show you that you can have a good separation using the chromolith technology. Alright, and another technology that is being developed is a core shell technology, whereby it's a more of a hybrid type material, and this core shell is the latest technology that I know of. Alright, so what are the differences between a core shell and a monolith, or a more typical or traditional porous silica? I will show you a picture in the next slide. Okay, so it's a higher chromatographic performance, meaning efficiency, versus those of a fully porous silica, for example the monolith or even the traditional ones. So it made of a solid non-porous spherical core surrounded by a porous shell layer. So in contrast to the traditional ones, whereby you have spherical silica and it's porous everywhere, now for a core shell is that you still have the porosity, but it's only on the outer surface. So by doing this, what you are actually reducing is you are reducing the void volume inside the column. Okay, at the same time you can still play around with particle size, you can still play around with the porous size and whatnot. So you can have the advantage of all the traditional ones, at the same time you have an additional advantage of reducing the void volume. Okay, so this is how the core shell particle looks like. So you have a non-porous silica and a porous silica, and you can actually see from this electron microscopy images that even though the picture is not as clear, but you can actually see that is the core, which has little or no porosity at all, compared to the second layer, which has a lot of pores. Okay, so this is what they call as pore size technology. But again, of course, if you actually zoom in over here, you might be able to see a very very tiny small holes, but you know, I'm not going to touch on that. And what we can see is that they are actually porous molecule. Okay, something is off with this, so I will need to stop mirroring and do it again. Right, apologies for the alright. Okay, now it goes back to full size. Okay, and to show you the difference between this core shell technology is these two different columns. They are both helix columns, so you know that it comes from the same company. Okay, but one is a pore size, a core shell, the other one is the normal ones. And by looking at this, you can have a guess which one is core shell. I give you 5 seconds. 4, 3, 2, 1. Yep. So the core shell is, my wife is smiling over there at the side of the room. The core shell technology is the one at the bottom, because you can see now the resolution is improved. Okay, there's no particular reason why you want to introduce a technology that does not improve the column altogether. Okay, now you can see the resolution improved, even though you might say the efficiency now is lesser, because previously it takes you less than 0.7 minutes, now it takes slightly longer than 0.8 minutes, but the resolution that you can get from using a core shell outweigh the disadvantage of running slightly longer cycle time. Okay, so that is the example. You can just read the figure legend down below, and that's it for column technology. Okay, And for lecture 4, what we'll be focusing on is method development. So if say you want to you want to create a method for whatever reason, if say you are just starting to work with HPLC, you need to know how you actually create it. So it's more or less the same as gas chromatography, but of course, because this is no longer gases, there are some differences that you need to take into consideration. And then we will probably look at troubleshooting, some examples of what issue might have occurred, or that issues that you might encounter, and how do you actually tackle the issues. Okay, so that's for lecture 4. These are some examples. Some photos are licensed under Creative Commons, so you know, if you are watching this lecture but you are not part of UM student and the picture that I've used is not being referenced, do let me know, and I will do my best to actually acknowledge the images. And that's it. Thank you, and I'll see you guys next week. So next week we will have a live lecture. I'm hoping that you have submitted your assignment before you actually attending the lecture. So because the lecture is more about troubleshooting, so you know, any questions that you are wondering, or if you are actually working, doing a part-time, or you are still, even though you are a full-time student but you still want to go to your company to do some work, or your boss requests you to do something, and it's not being covered so far, you can probably ask it during the troubleshooting lecture. Okay, all right, I think that's it. Thank you and have a wonderful weekend.